Okay, now that computer is back, remember, last time we saw how difficult is calculating Riemann sums. And then one of the things to do a bit more on the definite integrals was to study properties. We have studied properties related to the integrand, linearity. We studied the properties related to the bounds, like a to a always gives you 0, ab is negative ba. You flip the bounds and then you get a negative sign. Also, you can break up your integral on different pieces and add them. So there is also another inequality property that I'll start with this before we go to the fundamental theorem of calculus. So this is called positivity of integral. What does positivity mean? It means that it works nicely with inequalities. If f of x is less than g of x on the given interval ab, then you integrate f, you will get a smaller number than you integrate g. Then integral ab of f of x, which is a number, is going to be less than integral of the upper one on the interval ab. Well, if f and g are positive, this is not difficult to see, because if f is less than g, that means that on this interval, the region under the graph of f is a subset of the region under the graph of g. So we are trying to find area of a smaller region. And that's why we would have that inequality. But one important application of this is, in particular, if a function is smaller than and bigger than two numbers. So if I have bounds, upper and lower bounds for my function, capital M bigger than my all values of f of x, and lowercase m all bigger than lowercase m, then in that case also we can apply this inequality. So we get integral of f of x dx. You apply it twice, yes? Integral of constant function. Well, we already know if it is positive how to deal with it. So if it is c here, we go from a to b. Integral of c on the interval ab, this is the area of this rectangle, yes? And that area is nothing but b minus a times the height, yes? For this m, which is a constant, the height is m, the base is that. For this one is lowercase m, like that, okay? So it says that if a function is between two constants, then those two constants will give us bounds or upper lower bounds for the integral of our function. In other words, it will keep our integral, the value of integral, between two numbers. It's not really approximation, but it kind of tells you something about the integral. It says that this integral cannot go beyond that number, cannot go above that number, yes? And that we will try to use in some examples. For example, we know cosine squared x. We go from 0 to pi dx. Cosine integral of cosine square, if you want to find that, you actually need to do few works even after I introduce fundamental theorem of calculus. And actually the place that you will be evaluating this thing is the second calculus. If you take 1301, you will see how we evaluate these ones. It's not very complicated, but it's not straightforward. I don't know how to evaluate that, but what I want to use is that, can I use those inequalities to find a limit for what would this integral be? Well, let me do this example, and I'll write 2 more examples for you to complete. So here I say that cosine x everywhere, including intervals 0 to pi, goes between 1 and -1. Indeed, those are actual bounds for our function. And then if I square these guys, I get cosine squared is going to be always less than 1. Also, cosine squared, if I square it, it will be always bigger than 0. Yeah? There's a bit of tricky game there I'm playing. I'm not squaring this other side because squaring doesn't keep the inequality the same direction if the numbers are negative. If you square it, it will flip around. Now, I have lower m, upper case m. From that fact that I had over there, I can conclude that my integral will go, well, it will have a number, it will have a value, but that value is going to be between lowercase times b minus a, lowercase m, 0, times pi minus 0, upper capital M, pi minus 0. In other words, we know that our integral will give us a number between interval 0 to pi, nothing more than that. Any questions, any comments before I write that remark down? Of all such capital M and lowercase m for any given function, there is one that we already studied. One can take capital M. All the values of function are less than or equal to that. Do you remember what kind of value was that? We have a name for it, actually. Yes? Upper limit of what? OK, we have a name for it a bit more precise, actually. Yes? So what you're saying is the upper bound, sometimes we say, but that's, again, that's the name of m here, the way we are using. But there's one out of all these which works better. This is absolute max value. M could be is absolute min value. In both cases, of m on the of f on the interval AB. We know that absolute minimum value is the value which is smaller than or equal to all other values of the function in that interval. And absolute max is the value which is bigger than all of them. So then the next example says, use absolute max and min values to find limits or upper lower bounds for given function. We can actually find those capital M and lowercase m. The first one is f of x e to the power this on the interval 1 to 4. The other one is f of x is x cubed, x squared minus 4x on negative 1 and 3. Use absolute maximum value of the given function for bounds for given integral. I should have written basically integral of e to the power minus x squared dx from 1 to 4, and the other one integral of that function from there. What I mean is that with the knowledge, with the skills you have created so far, you can find these lowercase and capital case m. For each given function, we are working on a closed interval. You can use that inequality to find the techniques you know to find the absolute maximum value of the function on the given interval. And the absolute max is going to be playing the role of capital M. Absolute min is going to play the role of lowercase m. Okay? Go ahead, I'll give you 90 seconds, and I expect you to be able to find absolute maximum of both of these functions on the given intervals, and hopefully start working on the inequality for the given, at least one of these given integrals.
I think here's what I think. What is the restrictions on this function? So actually we can rewrite this as we can rewrite it as this. We know. So what is that? I mean it can't be 0.
You have 30 seconds left. Find the derivative of e to the power negative x squared, set it equal to 0. What are the critical points there? Critical points of that function. I want to hear that. Come on. I'm not leaving. Critical point of that function. What were you doing then? I could see some of you just chatting about different things, but most of you were busy. What are the critical points, please? Yeah? 0. There's only one critical point for this function. That's 0. But here I'm not, the 0 is not in this interval, so that critical point, we have to throw it out. And then I evaluate the function at the two endpoints. One of them will give me absolute max. Which would be negative e to the power negative 1. The other one will give me absolute min, which is e to the power negative 4 squared, which is 16. I can take this one as capital and this one as m. In other words, what we have shown is that the function e to the power negative x squared is between e to the power negative 1, I'll write it as 1 over e. E to the power negative 16, I'll write it as 1 over e to the power 16. This is not true for all x's. This is true for x's in 1 to 4. Yes? So for x's in 1 to 4, f of x gives you those values. And then right away from that, I can conclude that the integral of that function would be, oh, wait. I did write this other way around. This 1 over e to the power 16 is absolute min value, so it should go there. 1 over e goes as absolute max. I said everything right, but I wrote it wrong. So capital M times b minus 1, that's 3, lowercase m times 4 minus 1, 3. So my function will be between 3 over e to the power 16 and 3 over e. Any questions, any comments there? We should move back to this one. Yes, what? B minus A. Look at the inequality. M times B minus A. B minus A, 4 minus 1. That's 3, yes. Okay. This one, I want to find the absolute max and min. I find the derivative. Set it equal to 0, x is equal to 2. That's the critical point. I need to evaluate the function in 3 points. If at negative 1 will give me 1 plus 4, 5. If at 2, it will give me 2, 4 minus 8, negative 4. And I'll evaluate it at the other endpoint, 3. 9 minus 36? Yeah. 9 minus, oh, no, not 36, minus 12. 9 minus 12. That is negative 3. Then this is absolute max. Capital M is absolute max. Absolute max value, which is 5. M, lowercase m, is absolute min value, which is the lowest one, negative 4. If I want to write this in a different way, is f of x is between negative 4 and 5 on what interval? Interval negative 1 to 3. On the interval negative 1 to 3, our function is between negative 4 and 5. Then its integral from negative 1 to 3 is not going to be between 5 and negative 4. It's not. It's going to be between negative 4 times b minus a, 5 times b minus a. Without integrating, that's a piece of information I can use if someone says that, okay, at least tell me how big or small this number is, this integral. I don't need to find the exact value, but I can tell them that this integral would be between negative 16 and 20. That's piece of information we can find. Yeah? Are we good? Any questions? Any comments? Yes, please.
How did you get the critical value for f of x equals e?
Derive negative 2x e to the power x squared equal to 0. e to the power negative x squared cannot be 0, so x must be equal to 0. Negative 2x e to the power negative x squared. There's only one critical point, but that critical point is not in this interval. So I cannot use it to determine absolute max and min. The only two things remaining there are the starting point, end point, right end point, left end point. Remember, for the critical, for absolute max and min, we find the critical points inside the interval and two end points. Yes, there's no critical point, so there are two end points, 1 and 4. One will give you absolute max, the other one will give you absolute min.
How do you find it to be 0?
Oh, the derivative of that set is equal to 0, yeah?
No critical.
This guy is always non-zero. E to the power, any real number is non-zero, so 2x must be 0. So x must be 0. Yes, sir. Yes, please. Louder, please. Yes.
When you write like m times b minus d, do you just leave it at that, or can you like?
No, you just evaluate these ones. I'm just leaving it. Come on, I'm running a show here. This is about the show. Yes, now you force me to do that. Yes, you have to write the number. No. It's just like me. It's like, cool, isn't it? Okay. I think the positivity of integral was the last property of the integrals before the big guns come in. Fundamental theorem of calculus. I'll just write FTC. Fundamental theorem of calculus. It has two parts. It has two parts. Today we are going to cover part 2. Before I start, I decided to do part 2. So before I start that, I want to remind you that all the pain we have taken from this last week, when we started Riemann sum, the area, that summation, find limit, yes? I hope that I have been able to show you that that definition, even though mathematically is a precise and nice definition, but practically, evaluating integral by those sum or Riemann sum, limit of Riemann sum, is almost impossible. We could only do for simple cases, for few simple cases, yes? So that was why we moved away from the definition to the properties. We tried to figure out what is the relation between the integral and area. We did also work on symmetries of integrals so that we can simplify and evaluate some integrals. And also, well, today's thing, like you could see that, okay, I'm simplifying, I'm not getting the value, but I can give you some estimates of where my integral is. But none of those are the actual game when it comes to the evaluation. And as you will see, most of them would be a side result or side fact that we will use after we understand fundamental theorem of calculus. What is fundamental theorem of calculus? Let me write it down, and then there's a few things that we have to discuss. What does it mean? Why we are doing it this way, all those. Fundamental theorem of calculus goes very simple. It says we want to evaluate integral f of x dx from A to B. Mr. or Mrs. FTC comes in and says that, oh, don't bother thinking of Riemann sum, limit, all those. What you need to find is one antiderivative for the function f. Let f be an derivative of the function, the integrand. Well, I play in that interval, okay? Don't mix things up. Antiderivative, you remember what does that mean? Is a function whose derivative is equal to this function, yes? It's about derivative, going backward in derivatives. It says, if you know one antiderivative of that function, evaluating definite integral is easy. We write it this way. But what does that mean? It means this. You evaluate the antiderivative at the upper limit minus evaluated at the lower limit. Evaluate the function at the upper limit minus evaluated at the lower limit. This way, computing this integral is not anymore go find Riemann sum and the limit of Riemann sum. It's about finding antiderivative. And why this is called fundamental? There is a reason. You don't call any theorem that passes by a fundamental theorem of something. This comes from the fact that, remember, antiderivative is coming from the world of differentiation. It's backward operation of differentiation. Integration comes from that Riemann sum world. This is about area. We are finding area. This one, I'm differentiating. To start with, there was no expectation that these two things should be related. And why should they? This is about derivative. Remember, there was this completely different story about that. The other one is integration. So before this theorem, our calculus was a land on two islands, completely disconnected. There is this story of find area, Riemann sum, find limit of that. The other one was derivative, and then go backward, find an antiderivative. What this theorem does is bridging between these two things. It says that even though to start with they would look very far away from each other, disconnected, but these are related by one this way. If you know antiderivative of integrand, you can do that whole Riemann sum, pass all Riemann something and evaluate that. The fundamental theorem of calculus part 1 goes the other way around. That's something that I'll discuss on Wednesday. But I want to make sure that today when you go home, while you're walking to home, if you remember suddenly, oh, we studied fundamental theorem of calculus, you should stop, pay respect. Thank you, fundamental theorem of calculus. I want you to appreciate what this thing can do for us. It's not a simple calculus theorem. No, it is about two completely separate useful knowledge of humankind connected with this thing. When you say fundamental FTC, you thank the who? I don't know who. The God, the godness of mathematics who created this bridge. Don't take it simple. If you go home and you say that, oh, FTC is easy, go wash your mouth, come back. Think about it again. It's a serious thing. Calculus, unfortunately, has been cleaned up so many times that we usually say, oh, look, FTC, antiderivative is nothing but indefinite integral. Well, obviously, it should have something to do with the definite integral. No, to start with, it wasn't. To start with, they were completely different stories. And after we figured out they are related, we chose this notation and that terminology for this guy. Otherwise, they were completely two different things. Were I successful enough to emphasize how you should pay respect to this theorem? Yes or no? Yes. Thank you. Let's see this in practice. Let's see this in practice. That integral that this integral that we already did, find where it should stay. Now we can evaluate. We can evaluate using FTC. Why? Because I know I can find antiderivative for this guy. We actually have a whole bunch of rules for antiderivatives. X to the power n has antiderivative x to the power n plus 1 over n plus 1 minus this guy. Yeah? Fundamental theorem of calculus says, well, choose only one of them. You don't need to choose all the antiderivatives. So I will choose x cubed over 3 minus 2x squared, go from negative 1, 3. That's just just notation. The meaning of that notation is plug in 3 there. So 3 cubed over 3 minus 2 times 3 squared minus, plug in this guy there, negative 1 cubed over 3 minus 2 times negative 1 squared. (27 over 3, that is 9, minus 18 minus negative 1 over 3. This is 2, negative 2. That is negative 7 over 3. Yeah? That is negative 9 plus 7 over 3. Then that is negative 27 plus 7 over 3. And that is negative 20 over 3. It's really negative 20 over 3 between negative 16 and 20? Yes, it is. If I did all the calculation right, that's another confirmation of that. That will work out nicely. Before I go write down some examples, we have a whole bunch of examples we have to do. One question comes up here. This says you use only one antiderivative. But when we were working with the antiderivatives, we knew that there are a whole bunch of antiderivatives. And we actually know that every two antiderivatives differ by a constant. They're different by a constant. Now the question is that, what if I use a different antiderivative? What will happen there? Would that give me a different value for my integral? What would go here if instead of this antiderivative, I would use the antiderivative plus 2? Well, since we are subtracting, the constant c is not going to play any role there. So f of x plus c, go from a to b, means evaluate b there. So f at b plus c minus f at a plus c. Yeah? My c minus c, they will cancel each other. We get f at b minus f at a, which is the same thing as f at x, go from a to b. Doesn't matter. When you're using fundamental theorem of calculus, you can actually always drop that plus c. Drop it and then do the work that fundamental theorem of calculus say. we have to write down where we are using fundamental theorem of calculus, as we have been doing for any other important theorem with name. You have to cite it. Why does this happen? Because of FTC. How about you evaluate integral from 1 to e of x cubed plus 1 over x dx. Also, I'll give you only 1 minute. Only 1 minute. I'm sure that you will be able to complete one of them and evaluate the other one for an antiderivative. Go ahead, please. Because it has two parts. There's part 1 that we'll cover on Wednesday. Yeah? I can separate these denominator on the numerator terms. So x cubed over x, this is x squared, plus 1 over x dx. We go from 1 to e. This is definite integral, but fundamental theorem of calculus says if I can evaluate, if I can find an antiderivative of this, I'm good with evaluation this way, that antiderivative of this is x cubed over 3 plus, what's antiderivative of 1 over x? Ln of absolute value of x. Since I'm using fundamental theorem of calculus, I actually don't need to write plus c. I'll go from 1 to e. And then that the rest means this notation means plug in this value into your function, e cubed over 3 plus ln of e, minus plug in this value into your function. And then subtract the second one from the first one. So here, this is 1, this is 0. This is 1 over 3. 1 minus 1 over 3. That's 2 over 3. So e cubed over 3 minus 2 over 3, which is the same thing as e cubed minus 2. I can now play the same game here, but this is called fundamental theorem of calculus, part 2. Antiderivative of 3x is 3x squared over 2. Antiderivative of 1 is x. What is antiderivative of 1 over 1 plus x squared? Yes?
Why did ln 1 and ln 2 cancel each other?
Sorry, why? Why did what?
E and ln 1.
Ln e is 1. The value of ln e is 1. Ln at 1 is 0. The value, I'm putting the values of these functions in.
Yeah, but you...
Okay, I hope that's solved. Back to my question. What is antiderivative of 1 over 1 plus x squared? Yes? Oh my God. When I'm asking questions, is there any question? No one answers that. Okay, let's see. What was your question about this one?
Would that be positive 2 over 3?
You're right. Thank you. Yes. Yes, there is a, thank you. You stopped me for a good thing. Thank you. Okay. I'm asking this question for the third time. Antiderivative of 1 over 1 plus x squared. Yes, please. Thank you. I have been looking for that. It wasn't in my drawer. Tan inverse of x, and we go from 0 to 1. Yes? And going from 0 to 1 means evaluate that 1 squared over 2 plus 1 plus 2 tan inverse of 1 minus, evaluate at 0. 0 squared, 0 tan inverse of 0 is, tan inverse of 0 is 0. So this whole thing goes away. This is 3 over 2 plus 1, that is 5 over 2. Oh, this is not negative, this is positive. Sorry, this is not positive, it is negative. Sorry. What is tan inverse of 1? Pi over 4 times negative 2. Any questions, any comments there? Well, now that I know how to evaluate things, I can go ahead and use this fact to evaluate area under the graph of some positive functions. Example, find the area under the graph of given function on given interval. Sin x on 0 to pi, 2 to the power x on 1 to 2. I'll only give you 30 seconds to wrap your head around this, and then I start.
Don't be anti-Jewish.
Indefinite integral. That's the notation, yes? Indefinite integral is the notation. Okay. Remember that when your function is positive, like sin x on the interval 0 to pi, the area, we saw this in practice, the sum, the limit of the Riemann sum that we use to evaluate that area is the same thing as Riemann sum for the definite integral. So this is going to be given by this integral when the function is positive, yes? But so far, I didn't have any simple way to evaluate that definite integral. Yes, I know that's going to be defined by Riemann sum, but there is no way I can evaluate that Riemann sum. Well, now I have a stronger tool, FTC2. It says, find antiderivative of sin x. What is antiderivative of sin x? Negative cosine x. And then go from 0 to pi. Meaning that evaluate your antiderivative at pi minus evaluate your antiderivative at 0 and subtract the second one from the first one. Cosine of pi is negative 1 minus 1, so I have negative minus 1 minus. Cosine of 0 is 1, and there's a negative sign there. Altogether, this is equal to 2 to the power x. All exponential functions for real functions are positive. Well, before we have done Riemann sum for this kind of integral, and this is an example of Riemann sum that you have to be able to evaluate and find it. But now I don't really need that, because area is given by this integral. And I know what is antiderivative of 2 to the power x. What is that? Oh my God. You come back on Wednesday after you review your antiderivatives. I will review as well. It's not 2 to the power x. It's 2 to the power x over ln 2. And by this means 2 to the power 2 over ln 2 minus 2 to the power 1 ln 2. That is 3 over ln 2. Well, we will be using a fundamental theorem of calculus. It means that you have to review your knowledge of antiderivatives. Come back on Wednesday. We will do more integration. Have a great day. See you all Wednesday.